XPS or electron spectroscopic chemical analysis. It is abbreviated XPS or photon in, electron out technique, so that to determine the surface composition and chemical state. Ejecting the electrons from the material and through we XPS plot function of binding energy. So XPS is able to determine surface composition and chemical state, so that we can see the oxidation state of an atom, whether it is neutral ion, 0 neutral ion, or +2 ion, or +3 ion, or the binding energy increases as oxidation state increases from ion 2 plus and ion 3 plus. So increasing the binding energy, given the increased as the positive charge on the ion increases. Very sensitive technique and highly sensitive, 100 atomic or monolayer complete, we are able to detect it surface, and very lower, only 1% full of atoms on the surface. We are able to detect that new foreign material on the surface, 1% sensitivity there by atom population. So it's chemical state specific of each element, and it has own fingerprint region for each element. We could calculate the binding energy for each element. 1s binding energy would be, and 2s, 2p for nitrogen as unique spot on the x-axis of the binding energy, and we are called as a fingerprint for the nitrogen. And likewise, all other elements of the periodic table have exact positioning. So it's 403 electron volt or 404 electron volt of for nitrogen 1s can speak to the oxidation state of the nitrogen. So it speaks about the chemical environment and the atomic oxidation state, whether it is charged or non-charged, and covalently bonded materials. So we can get different oxidation state information. We need to measure the electrons along the mean free path in order to determine the kinetic energy. So we can't have electrons scattered off their path to the detector. So we need very ultra high vacuum for this technique, and the technique to work in order to quantify the speed of these outgoing electrons. Since we are using X-ray excitation to emit the electrons from within the atoms, we can expect some damage to the surface, and often to have a very careful measuring certain materials. Copper, for example, is known to change as you integrate with the XPS. So if you have gotten a certain oxidation state in your copper metal, that might be changing as you apply X-rays to understand the X-rays XPS spectrum. So you have to be very careful in analyzing the copper. So we need ultra high vacuum. The pressure we need is 10 to the power of -7 to -7 torr, or if you want to convert to Pascal, it is 10 to the power of -5 pascals, or we very low pressure, ultra high vacuum technique, and use a turbo pumps in order to off an hour, or to get this vacuum in order for this instrument to work, and with Lagrange the mean free path of the excited electrons to take it to the detector without scattering of that pathway. Another technique is mentioned is very surface sensitive, and so any contamination present in the surface, very handling by the engineering using gloves, or scientists you need to use very handling properly. Just processing the material in its fabrication can be a dominant characteristics in the X-ray spectrum. If one is not careful and with the prepping the surface, it's a very contamination. You need to have the surface is very clean, and so avoid surface contamination. Okay. So this XPS instrument that you need high energy reactions, X-rays, to get the electrons ejected out and can change the material so reactions can be possible in sort of oxidize also material by way of the X-ray excitation. So okay, this is surface sensitivity. So surface sensitivity is we know that the incident X-ray can penetrate into the material for about 1 to 10 nanometers in analysis depth and will give rise to ejected electrons from that area, particular area where is X-ray is excited. So while there may be a complex structure in this topmost surface, we are going to see that average in the resulting XPS spectrum. So materials directed as deeper as 10 nanometer can show up your binding energy graph, that is XPS spectrum. So by getting this, not only the penetration depth of the X-rays, but of course our ability to have electrons escape from that surface and tends to be the sampling depth limiting factor. In fact, the escaped depth from this electrons getting out of the material shows the characterization of the talcum powder, or talcums that can be added to the plastics for easiest. This is a talcum powder, XPS of the talcum powder. Added plastics for easiest to processing, a bit of slip, lower processing temperature. So temperature and pressure. So this characterization, we can see that oxygen has been detected in two different spots. There is two different orbitals, oxygen, where we can eject electrons, and we also see magnesium showing a couple of spots, and then and in addition carbon here allows to relative composition to be determined, and then almost the carbon accounts for relatively 11% of carbon, around is 11% of carbon, and then oxygen around it's sixfold than the carbon, 60%, 58.8% of oxygen. Show that we have seen this peak shift in the oxygen has been two new binding energies, and we understand the change from the neutral state to more oxidized state of the surface. So new material, and we can have binding energy, and we can look at the corrosion. So which tends to the convention XPS. We normalize the intensity. We place the tallest peak at the value of the XPS. Now I'm speaking more to the oxidation state. Get from the XPS. You can see that not reversed x-axis. Binding energy shift in the conversion in XPS. No intensity. Higher value of 1. So 0 to the lead, you can see for the intensity from 0 to 1, and you can see the lead 2 plus in the 2 option, lead 2 plus. Not only that, lead 2 plus in 2 different signals. In the ionic compound with sulfur and fluorine, those are the neighboring atoms to complete this ionic compound. So lead sulfide, lead fluoride, and lead sulfate, and we can see the shift in those materials with different binding energies. So we can have a complex mixture of lead, but we are able to fit the graph to try the determination of the quality of lead, 0 lead, and higher oxidation state, lead 2 plus, and this is able to understand the chemical state, whether the oxidation state, and then from neutral elements, and then with that lead sulfide, lead fluoride, and lead sulfide, relative composition, and then magnification range of the x-axis. So we use the area to determine the relative composition of the material and focused on the composition, which is specific composition for each lead. We have the area also different. So immediate energy cast by the anions. So here there is one and is XPS of nickel metal, nickel oxide, and nickel hydroxide. One is nickel metal is in 0 oxidation state, nickel oxide is in 2+, and nickel hydroxide is in 2+. So both shifted in the binding energy. In short, the fitting curves are mathematically added, and you are applying the fitting curve. You are applying the fitting curve to represent each area. You fitting the curves, so that you can look at fittings graph that we need to recreate it. Expected split into signals 2+, binding energy, mathematically added, fitting curve to give ideally on the top of the experimental curve shown in the dark black. Determination of the composition numbers we see reported here. We also note that signals tend to split in the case we handle for P, D and F orbitals, and this is the what we can call spin orbital splitting. And so the values of the splitting have a core level of element about the same. So we can see the spin orbital splitting splitting the 0 to is about the same way you can see for the higher oxidation state. And okay, now